Today, we're going to do one more example involving friction, tipping, and multiple bodies. And this is actually a pretty challenging problem. What we've got going on is it says we have a uniform. Remember, uniform means we're going to put the weight right in the middle. It has a mass of 6 kilograms, so we'll use that to find the weight. Slender means we're not going to worry about how thick this is, and so we're just going to treat it as though it's kind of a straight line. It doesn't have any width, really. It rests on top of this gray block, which we're told is 3 kilograms. That's its mass. And we have frictional contact at 3 locations. Point A down here on the ground, point B where the rod and the block meet, and point C up here. And we are asked to find the largest couple moment before something starts to move. We've got a few different possible motions. We'll get to that in a minute. This kind of problem, typically, you're going to want to break things apart. So draw a diagram of just the rod, and then we'll do a diagram of just the block. We'll write out our equations, figure out how many unknowns we have, and then look at the different possible motions to decide whether we assume sliding or whether we assume tipping. So I thought it made sense to start with a free body diagram of one of the objects. I drew the rod first. So free body diagram of the rod. It has an applied couple moment, M, and at the middle, it's got a downward weight, mg. The mass is 6 kilograms. G is 9.81 meters per second squared. And multiplying that out so we can just use it throughout the problem, we get 58.86 newtons. Now at point C, it's resting against a wall. So the wall is going to provide a perpendicular or normal force at C. And then there will be a friction force. So to figure out the direction of the friction force, can you see that with this clockwise applied moment, that would tend to cause the rod to rotate clockwise? In order to rotate clockwise, the point C is going to have to move down the wall. The friction at the wall has to oppose that motion, so the friction force at C will be up. Now at point B, it's resting on a surface, so the surface will apply a normal force perpendicular to the surface. And then by the same reasoning, if this is going to rotate clockwise, that means point B would be moving to the left. So we will end up with a force of friction at B to the right. It has a lot of unknowns. I count 5, 2 at point C, 2 at point B, plus the applied moment that we need to solve for. So let's write out our equilibrium equations. We know we won't be able to solve because we have 5 unknowns, but let's get them written out. If we sum forces in the x, we get an equation that says the force of friction at B to the right minus the normal force at C to the left has to equal 0. That's equation number 1. Now we're going to sum the forces in the y direction. Doing that, we get the normal force at B is upward, the weight, 58.86 newtons, is downward, and then the force of friction at C is upward, and those have all got to add up to 0. So there's equation number 2. And then finally, we need to sum moments. You can sum a moment anywhere you'd like. I chose to do point B simply because we have 2 unknowns at B. It doesn't really make the math any easier versus if you summed it at C instead. So applied moments, first we've got an actual applied couple moment, M, that's clockwise. So we'll have a minus M. Also, the weight will cause a clockwise moment about point B. So 58.86 newtons, and I need perpendicular distance. So the force is vertical. That means I need this horizontal perpendicular distance. The whole width is 600 millimeters. So a force that acts at the middle would be 300 millimeters away. I'm going to write that as 0.3 meters. If I only had forces times distances in here, I'd probably just leave it as 300 millimeters. But I probably want to get the moment in units of newtons times meters, not newtons times millimeters. So we'll just convert everything to meters in our equation. Normal force at C will cause a moment about point B, and it's going to be clockwise, and that perpendicular distance would be 800 millimeters. So I have plus NC times 0.8 meters. And then finally, I have an upward force of friction at C. So if you go right 600 millimeters and up, that's going to cause also a clockwise moment. So plus force of friction at C times 0.6 meters equals 0. That is my equation number 3. And we have 5 unknowns, 3 equations. I'm not going to bother trying to solve at this point. To make progress here, we need to do a diagram of the other part that's contacting this. So let's do a diagram of the block. It is a rectangle and it has a weight in the middle, mg. Its mass is 3 kilograms and G is still 9.81 meters per second squared. And we get that the weight is 29.43 newtons. The surface on top right here is the same surface that was interacting with the rod. These are the forces that the block applies to the rod. Well, the rod applies equal and opposite forces back on the block. So I'm going to have to the left force of friction at B and downward the normal force at B. So those are our equal and opposite pairs. We got that one to the right, this one to the left. That normal force at B upward, this normal force at B downward. Just like with a frame or a machine, you've got two things in contact. So when you take them apart, the force that one exerts on the other is exactly equal and opposite to on the other side of the surface. Okay, what about the bottom of this block? There's a frictional interface at A. And so we got to think about which way the block's going to move. Well, because the rod on top is pushing the block to the left, that means that this ground has got to resist that motion. So our force of friction at A will go in the opposite direction compared to the force of friction at B. And now we need to apply the normal force. Because we have dimension this problem, I suspect one of the possible motions is going to be for this block to tip over rather than sliding. So the way you analyze tipping is you need to not draw your normal force just anywhere. You want to draw the normal force at a specific location. And I don't know the location. So I'm guessing that because this force is tending to make the block over, the normal force is going to shift left of center somewhere. So we'll have a normal force at A. And what I want to draw on here as an extra additional unknown is the distance, X, how far away that is from the center line of the block. Let's write equilibrium equations for the block. So let's sum forces in the X direction. Doing so, I just have the two friction forces. Force of friction at A minus force of friction at B is equal to 0. And there is a fourth equation. Next, let's sum forces in the Y. And doing so, I get force at A is upward, the weight is downward, minus NB equals 0. And that would be equation number 5. Next, we can sum moments about a point. And I think I've told you guys in class, the point I really like to sum moments about on tipping problems is right there. Call it point O. The ground on the surface where sliding could occur, but straight underneath the weight. So if we sum moments about point O, here's what's nice about it. Most of our forces won't contribute to this moment equation. The weight goes right through it. NB goes right through it. Why do we know where NB acts? Because NB is the interaction between the rod and the block, and we're told that the rod lands right in the middle of the block. The normal force at B goes right through point O, and the friction force at A also goes right through point O. So this equation will only have two things in it. It's going to have the force of friction at B times its distance away from point O, and that should be the height of the block, 300 millimeters, 0.3 meters. That one is going to be counterclockwise, and then clockwise of the normal force at A times X, all has to equal 0. That would be my sixth equation. Now let's just count up our unknowns. At point C, we had friction force at C and normal at C. At point B, we had friction force at B and normal at B. At point A, we have friction force and normal force. And then we also have our applied couple and the distance X. So counting 8 total unknowns, and we have only written down 6 equations. So what that means is, in order to solve this, possible motions where we have kind of 2 motions happening at the same time to give us 2 more equations. So let's talk through what the possible motions are. The 3 that I thought were fairly reasonable, we're looking for the largest couple moment M before we cause motion of the rod. So one possibility is the block does not move at all. And then in order for the rod to move or rotate, you're going to need to have point C slide down the wall and point B slide left. So you'll have to have slipping at C and B simultaneously. So there's possible motion number 1. Slips at C and slips at B. So only the rod moves. If it slips at C, we're going to use that the friction force at C is equal to the coefficient of friction at C times the force at C. And then we'll use that the friction force at B is equal to the coefficient at B times the normal force at B. And this is one of our possible motions. Might happen, might not happen, but that would give us 2 more equations. This would be then your equation number 7, equation number 8. 8 equations, 8 unknowns, we can solve for everything. Another possible motion, what if instead of slipping at C and B, what if it stays C and only slips at C? Well, the only way that could work is if either this block slides so that B can move along with it, or you need this block to tip over so that B can kind of go over with it. And I think those are the only really simple cases that could happen, is you either don't have block B move at all, or you have it slide, or you have it tip. And in either case, you still got to slide up here at C. There's really no way for this rod to move without point C moving. I can't imagine any way that you would move B left or right that wouldn't necessitate C moving as well. So let's try those other two cases. The case 2 that I just mentioned is it still slips at C, but it doesn't slip at B. Instead, it slips at the ground, which is A. So then you would still use your friction at C equals coefficient C normal at C. So same equation 7, but then you'd instead for your equation 8, you use the friction force at A is the coefficient at A times the normal at A. There's 8. Case 3 assumes it slips at C and tips at A. So slipping at C is still a friction force at C is coefficient at C times normal at C. That's still equation number 7. And then tipping at A, the condition for tipping is when X is equal to 100 millimeters or 0.1 meters. So that's kind of your 8th equation. It solves for one of our unknowns immediately, right? Because tipping is NA can move farther and farther out to prevent tipping until it gets to the corner. And then if you push it hard on it, it's going to go over. So we have 3 possible motions. We get to pick one and solve. And I chose to do option number 3 just because we just learned tipping and may as well practice tipping again. So let's guess number 3 happens. We'll get an answer, then we can go and check where 1 or 2 would have happened instead. So if we guess that number 3 happens, we need to go and solve. So let me maybe copy down my equations and we'll do this step by step. I've copied down our 8 equations that we need to solve for. So the first thing I'm going to do is equal 0.1 meters to eliminate X right here. That'll get us down to 7 unknowns. And then let's see what our friction coefficient was. Force of friction at C is, I need the coefficient at C. Coefficient at C is 0.3. So we've got 0.3 NC as our 7th equation. So let's simplify this a little bit. So I want to take and I want to replace also my friction force at C up here as well as up here. And then I'm going to write down all of my equations. First equation doesn't have anything changed. Second equation has a force of friction in it. So that second equation is going to be exactly the same. NB minus 58.86 plus equals 0. Then our third equation also has a force of friction in it. It's got minus M minus 58.86 times 0.3 meters plus NC times 0.8 meters plus the force of friction at C. Well, that's 0.3 NC and that's times 0.6 meters equals 0. No changes in the 4th or 5th equations. So let me just copy those ones down. But our last equation will have a change. It's going to be force of friction at E times 0.3 minus normal at A times 0.1. So let's see if we can do some further simplifications. I think what I want to do is take this one and let's eliminate all of the NCs, right? This equation tells me that the friction force at B is equal to NC. So I'll plug that in and that will have eliminated NC from all of my equations. Let me write those 2 down. I'll end up with NB minus 58.86 plus 0.3 and then NC, that's the same as the force of friction at B equals 0. That third equation will become minus M minus 58.86 times 0.3 plus, now NC, let's actually combine those 2 terms. We have 2 terms with NC in them. Those can be combined. So 0.8 NC and then 0.3 times 0.6. So this is plus 0.8 NC, but I'm replacing NC with force of friction in B equal to 0. So that deals with all the blue equations. Now for the purple equations, the other thing I could do is use this equation to eliminate A or friction at B. But did you notice this is the only equation that has friction at A in it? So I'm just going to save this one. Once I find the friction force at B, I can just plug in there and solve for the friction force at A. So let's just write down my other 2 equations as I have them, copy them down again. So left with 4 equations and 4 unknowns, right? I've got M, friction at B, normal at B, normal at A. That's it. And it turns out, you notice that this equation only has M in it. So in fact, let's save that one for later as well. We'll just use that equation at the end to solve for the moment. So I really have got 3 equations and 3 unknowns. I'm going to also save this equation because it is the only equation with m in it, just like this is the only equation with a force of friction A. It's the other 3 that are actually kind of coupled. So let's use that third equation right here. And this is going to give us, if we solve for, say, the force of friction at B, it's equal to 1/3 NA, which we can then eliminate from the previous equation, and now we'll get down to 2 equations and 2 unknowns. What we're going to do is replace the friction force at B in that first equation. NB minus 58.86 plus 0.3 times 1/3 NA equals 0. And the other equation we're solving is that NA minus 29.43 minus NB is equal to 0. This is an awesome set. If I simply sum those 2 equations up, did you notice that the NBs will cancel? So let's add those 2 equations up. We add them, and what we get is 88.29 newtons with a minus sign. And then the NBs cancel, and I end up with 1 plus 1.1 NA equals 0. Solving, we have an answer. NA comes out to be 80.26. Now that we have an answer, this is a back substitution problem. If we just plug it right into the equation we just had, either one of these 2 equations, I will get NB. And NB comes out to be 50.8 newtons. Next, backing up to the previous equation, if I plug NA in right here, I will get the force of friction at B. Doing that, you get force of friction at B is 26.75 newtons. Now, I thought I used force of friction at B somewhere else up here. So this is using these last 3 equations. Let's back up and see. Oh, look at that. It's also equal to NC. Let's write all of that down. Friction at B is equal to the force of friction at A is equal to NC. So 3 things that are 26.75 newtons with this solution. And then we can solve for a couple of other things, but as far back as we really need to go is just to get the moment. Plugging into that moment equation, you get that the moment to cause this motion to occur is 8.56 Newton meters. Now this might be the right answer or it might not. So what we want to do is we had 2 other possible motions. I want to check them both. So let's check number 2. Remember what number 2 was? I don't remember what number 2 was. Possible motion number 2 assumed it slips at C and slips at A. We didn't assume it slips at A, so we need to check whether A is safe or whether it would have slipped at A. When we get done, we're going to need to come back and check whether it would have slipped at B or not for number 1. So check 2 means we need to check slipping at A. That's a friction equation. To find out what is the max friction at surface A. Well, that's the coefficient at A times the normal at A. Coefficient at A was 0.4, and the normal at A we just found was 80.26 newtons. Okay, multiplying that out, we get 32.11 newtons. Well, guess what? The force of friction at A is only 26.75 newtons, and since that is then 32.11 newtons, it does not slip. So far, our answer that we got that I put boxes up there looks correct because it doesn't actually slip at A. What if we check number 1? That would be assuming that it doesn't just slip at C, it also slips at B. So we're going to check what's the max friction at B. Well, that's the coefficient of friction at B times the normal force at B. Coefficient of friction at B is 0.6. And the normal force at B we just figured out was 50.83 newtons. Multiplying those out, you get 30 newtons. So now let's check. The actual friction force at B when the bottom block starts to tip over is 26.75 newtons. And since that is less than 30.5 newtons, it also does not slip at B. It doesn't slip at A, it doesn't slip at B. So our guess that it slips at C and tips is correct. Possible that you don't solve the right one first. If that happens, if I had, say, discovered that this friction force was not less than the maximum friction, what I want to do is actually scrap all of those pages of solving, go back to my original 6 equations. Remember the original 6 equations up here? We had 3 from the first free body diagram, 3 from the second free body diagram, and then what if we found that it actually slips at A? We need to go back and use these as our 2 additional equations instead of those as our 2 additional equations. And we would need to redo all of the solving process. 8 slightly different equations, basically 7 of the same equations, and the 8th one is different. So it's a totally different solution.